The first thing we want to do is consider what the domain of this function is. In this case, notice that x squared is always greater than or equal to 0, so the denominator is always greater than or equal to 1. That means our function is defined for any input values from the real numbers, so y is defined for all real numbers. And there is no restriction on our domain. The derivative helps us find the critical points, and it will be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. When you take the derivative of the numerator, the 2 here as the exponent will come down in front, times x plus 1, the quantity, the stuff, in parentheses, all raised to the first power, times the derivative of the inside, which will be the derivative of x plus 1 is 1. So we will get 2 times x plus 1 to the first power times 1, times the denominator minus the numerator times the derivative of the denominator. In this case, the derivative of 1 plus x squared becomes 2x, all divided by the denominator squared. There's a common factor of 2 and a common factor of x plus 1 squared. Oh, just x plus 1. So let's take that out. When we do this, what we're left with in the first term will be a 1 plus x squared minus, we still have a factor of 1 plus x remaining, and a factor of x. Continuing, that's divided by x plus 1 squared, the quantity squared. Now you can simplify what exists inside the parentheses by distributing both the x to both terms inside the parentheses and the negative 1 to both terms inside the parentheses. When you do this, you get 1 plus x squared minus x squared. Now there's a common term, an x squared minus x squared, that's going to add to 0 to give us 2 times x plus 1 times 1 minus x divided by 1 plus x squared. Since the denominator is never 0, y prime will always be defined, and to figure out when y prime is 0, we set the numerator equal to 0, and each factor in turn, x plus 1, gives us a solution of negative 1, 1 minus x gives us a solution of 1. We can now determine what the critical points are by plugging in the values negative 1 and 1 to the original function. This gives us critical points of negative 1, 0, 1, 2. So those are the first 2 important points on our graph. Next, we're going to look for the candidates for inflection points. To do this, we take the second derivative. Now, it's important to realize by looking at the last form we have of our derivative, if we were to multiply these 2 factors together, that is a difference of perfect squares, so that will give us 1 minus the quantity x squared. This is what I want to take the derivative of, and the derivative again will consist of a quotient rule. So we will take the derivative of the numerator, that's 2 times 1 minus x squared, times the denominator minus the numerator, times the derivative of the denominator over the denominator squared. In this case, when I take 1 plus x squared squared, I will now have 1 plus x squared to the 4th. So for the first derivative, I have the 2 carrying down times the derivative of 1, which is 0, and the derivative of negative x squared, which becomes negative 2x. This we multiply by 1 plus x squared squared minus 2 times the quantity 1 minus x squared. And when I take the derivative here of 1 plus x squared squared, this is a chain rule where the inside function is 1 plus x squared and the outside function is stuff squared. So dealing with the outside function, we bring the 2 down in front. That gives us 2 times the stuff on the inside, the internal function 1 plus x squared, to the first power, times the derivative of the inside, which gives us 2x. And then we have to divide this by the denominator squared. Again, rather than looking to multiply everything out, add like terms, and then factor, let's start by seeing what kind of factorization can happen in the numerator first. You can see that there are common factors of 2, 2x, and 1 plus x squared. So let's factor out a 4x times 1 plus x squared. When you do this, in the first term you're left with negative 1 plus x squared. In the second term you're left with minus, the minus from here, 2 times 1 minus x squared. And still we're all divided by 1 plus x squared to the 4th power. Let's copy our last line over to the next page and continue simplification from there. Within our brackets, we're going to want to distribute the negative sign and the negative 2. Distributing the negative sign here gives us a negative 1 minus x squared. Distributing negative 2 gives us a negative 2 plus x squared. We'll add like terms inside the square brackets. That will give us a total of x squared minus 3. Factor completely. So we get 4x times 1 plus x squared times x minus the square root of 3 times x plus the square root of 3, all divided by 1 plus x squared, the quantity squared. In this particular case, the denominator will never equal 0 for the same reason we saw before, because it's always greater than or equal to 1. But the numerator will equal 0 either when x is 0. This particular factor can never equal 0. X equals square root of 3, or x equals negative square root of 3. So that will give us our potential inflection points. So these are our candidates for inflection points. We won't know for sure whether they are inflection points until such a time as we check the sign to make sure we change concavity in the function. I've gone ahead and computed what the points are by plugging back into the original function and getting the outputs. So let's do the sign analysis. Our intervals are going to be from negative infinity to negative square root of 3, negative square root of 3 to negative 1, negative 1 to 0, 0 to 1, 1 to square root of 3, and 3 square root of 3 to infinity. You'll notice that I've put a black line here between places where the first derivative was 0. Those are the possible positions for the function to change from increasing to decreasing or decreasing to increasing. And I've put a blue line here between potential inflection points, and that's where the function has the potential to change from concave up to concave down. So I wanted to remind us both of what the first derivative was, that's what we calculated the first derivative to be, and what we calculated the second derivative to be. This is, of course, a sign analysis, so we can think about what's going on depending on whether x is less than negative 1, x is between negative 1 and 1, and x is greater than 1. And notice when x is less than 1, less than negative 1, when it's less than negative 1, the first factor here would be negative, the second factor would be positive, the denominator is always going to be positive, so negative times positive divided by positive is always going to be negative. Between negative 1 and 1, the first term is going to be positive, the second term is going to be positive, and the denominator is still positive, giving us a positive times positive divided by positive is positive. And when x is greater than 1, we get positive times negative divided by positive, giving us a negative sign. So we start decreasing, increasing, decreasing. If we do the sign analysis for the second derivative, in this particular case, when x is less than negative 3, we get a negative times a positive times a negative times a negative divided by a positive. So that's a negative times a negative times a negative divided by a positive gives us a negative. Similar analysis for the other intervals. When x is between negative 3 and 0, we get something positive. When x is between 0 and square root of 3, we get something negative. And when x is greater than square root of 3, we get something positive. So that means that we have a local minimum here at negative 1 as we go from decreasing to increasing. We have a local max at at x equals 1. And since the sign of the second derivative changes, we have inflection points at negative square root of 3, 0, and square root of 3. Finally, we need to do the asymptote analysis to see what the function's behavior is as it heads towards positive and negative infinity. So the limit as x approaches infinity of 1 plus x squared over 1 plus x squared equals, multiply out the binomial 1 plus x squared to give your numerator 1 plus 2x plus x squared divided by 1 plus x squared. Thinking about what's happening, the numerator is certainly going off to infinity. The denominator is going off to infinity. This is an indeterminate form of infinity over infinity. You might recognize it as a rational function and take the shortcut of looking at the ratio of the largest powers. But let's practice our L'Hopital by taking the derivative of the numerator, dividing it by the derivative of the denominator. It should have the same value as the limit as x approaches infinity of 2x plus 2 divided by 1 plus 2x. This also, if you do the analysis, as x heads off to infinity, the numerator is still going to infinity. The denominator is still going to infinity. It's still in an indeterminate form that can benefit from L'Hopital's rule. So again, we'll take the limit of the derivative of the numerator divided by the derivative of the denominator. And in this case, we get 2 divided by 2, which is just 1. A similar analysis will show that as x goes to negative infinity, the limit is also 1. And now we are truly ready to graph the function. Let's remind ourselves of the points we've already calculated. In particular, negative 1, 0, and 1, 2 were local extremes. 0, 1, negative square root of 3, which is about negative 1.7, and then when you plug that into the function, you get about 0.13, and approximately 1.7 and 1.89 are our inflection points. Let's plot those points on our graph. And remember, we have a horizontal asymptote of y equals 1, both as we come from negative infinity and as we go to positive infinity. So remember, in terms of concavity, our function is initially concave down, followed by concave up, concave down, and concave up. It is decreasing to negative 1 from